All right, hello everybody. This is the final presentation for the senior design project group, Auto-Extremity Robot Arm and Hand. And this is just going to be covering basically the workflow, the process, our progress, and of course showing you guys how we completed this project and the logistics of the whole thing. So that being said, getting right into it, the overview of the project or the objective was essentially to create a robot hand and arm that mirrors real-time human movements as captured through a Microsoft HoloLens. So that was the objective. And to do this, we had to separate the project into two parts because the robot essentially consisted of two primary components. There was, of course, the robot arm, and then separate from that, there was the robot hand. And so to attack this, the way we decided to split up the project and handle it for efficiency was by splitting up into two groups. So the first group handled the arm, which essentially meant controlling the movements and the communications and everything just for the robot arm. And this team consisted of four people: myself, Pablo, Vinny, and Jack. And then on the other hand, we had three members on the other team, which essentially controlled just the robot hand, doing the same thing with the Microsoft HoloLens. And this team consisted of Matthew, Austin, and Zavari. So that being said, every person had a different role in this group, which they played to. Starting with myself on the ARM team and, kind of going across both teams, I was just the general team lead and the project manager, managing deadlines, presentations, communications, and facilitating our meetings and things like that.
I'm Pablo. I was in charge of building the arm because when I received it, it was not constructed. And then after construction, I was in charge of programming the robot arm so it could relay from the CSV file and make the robot arm move with the data that we have acquired.
Hi, I'm Jack, and I was the back-end developer for the ARM team, and I was tasked with tracking the ARM movements using the HoloLens too.
So, hi, my name is Vicente, and I was responsible for writing up the documentations and basically keeping up with everyone and what their updates were for the project.
Hi, my name is Zavari. I was on the hand team. I was one of the back-end developers for this project. I was responsible for setting up our pies to connect with each other via network, as in socket connection, and as well as setting up server, and we also integrated with the HoloLens and the hand.
Hello, my name is Austin. I was a backend developer for the hand group, and I worked on most of the semesters was working on a custom hand tracking script. So I set up the HoloLens and the software development kit to use Unity and the VS Code, all that good stuff.
My name is Matthew Williams. I was the embedded systems engineer. So I worked directly with the hand and I programmed everything in order to get the hand moving as intended based on the feedback from the HoloLens too.
Yeah, so that's the team. And then going back to the project, the first thing we wanted to look at was the real world application, see exactly where this kind of technology could come in handy. And from our group discussions, we found four pretty critical points where we thought this technology could applicate to real life. Number one, general remote robotics, especially just being able to use a robotic limb from a distance and remotely, could be useful in different hazardous environments. For example, working in space or across drones or things like that, which have robot arms connected, we could essentially control that from a distance. A second, more major application would be in the medical industry, where things like surgeries or therapeutic movements or patients restraining motor functions could be essentially improved by using this technology and providing a way for, moving the arm around without necessarily actually moving it. Number three would be an assistive technology, which, as far as accessibility goes, perhaps people with disabilities could use these kind of robots or something to program movements which they can't do themselves. And finally, the most obvious application was industrial automation, meaning as far as these manual processes go in factories where people are still using their hands and in potentially unsafe working environments, it'd be a lot easier to have basically like a system like this where you could have something mirror your movements as seen through a HoloLens without actually working in the environment. So that being said, I'll pass it off to Vinny.
Let's start with the problem domain and our motivation. Our work lies at the intersection of robotics, XR technology, and human computer interaction. Traditional robot control methods can feel, clunky and unintuitive. So we asked, what if controlling a robot could feel as natural as, like moving your own arm? So that's our goal, enabling real-time, natural robot control through body movement. This has a wide range of applications from engineers working in complex environments to medical professionals and individuals relying on assisting technologies. All can benefit from smoother, more human-centric robot interaction. What drives us is the opportunity to solve challenging problems in real-time tracking, wireless communication, and robotic actuation using accessible hardware. Let's walk through the architecture that brings our system to life. It all begins with the HoloLens 2, where a user's hand movements are recorded in real time. These movements are streamed as data to our Raspberry Pi server. The server then saves and processes this data, forwarding it simultaneously to two clients, each responsible for a different part of the robot: the robot hand and the robot arm. Once the clients receive the data, they process it locally to ensure precise actuation. The robot hand and arm then execute the movements, mirroring the user's original actions. After actuation, feedback is sent all the way back to the HoloLens via the server, completing a closed loop system. This architecture ensures that our system remains modular, low latency, and scalable, which is perfect for real time natural robot control. And lastly, how did we stay aligned as a team? For communication, we used iMessage for quick updates and coordination. We organized our tasks using GitLab, where we tracked issues, assigned sprints, and documented progress. Our meetings were a mix of Zoom and in-person sessions, which helped us stay agile and connected. This combination of tools ensured smooth collaboration across all phases of the project.
Okay, so solution and technologies. As far as our data flow, the HoloLens was used to capture hand and arm movements. Then we used Unity with the mixed reality toolkit to interpret joint data for the hand. And we used a C# client app, which formats and sends data. And then Wi-Fi server on the Raspberry Pi to receive data. And then we had robot control code we used Python and C++, which this code had the main objective of moving the robot hand and arm. Then for tools and technologies, of course, we had the Microsoft HoloLens for real-time spatial tracking, Unity and the Mixed Reality Toolkit, a C# and the Net, which was the client-side communication app, socket programming, data transmission over Wi-Fi, Raspberry Pi, Python and C++ code, and custom robot hardware for the physical execution of movement. My part of this project was the hand tracking, getting the custom hand tracking to work with the HoloLens. So I created a script that created these spheres on every joint and tips of the fingers. And then on the left side of the screen, you can see all of the joint data moving in real time. And it will tell you if it's the left or right hand. That was my part. And here we have on the left the hand tracking script itself, and on the right the Unity project, what it looked like. Like I said, my main responsibility in the project was implementing hand tracking using the HoloLens 2, Unity, and Microsoft's Mixed Reality Toolkit. Setting this up was much harder than expected. Most of the online documentation was outdated, and I had to rely on a 4-year-old YouTube tutorial that didn't fully match our tool versions. A lot of my time was spent debugging and adapting old methods to work with the current versions of Unity and the Mixed Reality Toolkit. Once the setup was working, I created a script called Hand Tracking, which tracked the user's hand joint positions in real time. It also visualized the hand movement inside the Unity scene and recorded the data to a file called handtrackingdata.csv. Deploying to the HoloLens required using Visual Studio instead of Unity directly, which was another step I had to learn. At first, the CSV file didn't appear on the device at all. After some research, I discovered that the HoloLens restricts access to certain folders. A factory reset solved the issue, and I used the HoloLens device portal to retrieve the CSV file over Wi-Fi. After that, we successfully transferred the file from the HoloLens to a server and then sent the data to a Raspberry Pi. This completed the data pipeline. Our original goal was to have the robotic hand respond to this data in real time. While we didn't have time to complete that last step, the infrastructure is all in place for it to happen. I've documented the whole process, including tools, challenges, and advice for future teams, so others can build on what we've done without spending weeks in trial and error like I did.
Now on to arm tracking. Originally, our plan was to fully track the arm using crucial points such as the elbow, the wrist, and the shoulder, but due to limitations with the HoloLens 2, the only tracking built in was the hand. So we had to pivot and use the hand data in order to track the arm movements, which limited us to only being able to go up, down, left, and right because we only have 1 point to go off of. Whereas before we were hoping to have an elbow and move as an arm would. Also challenges with the HoloLens 2, since it's a Microsoft product and I have a Apple computer, the Mac OS would not seamlessly work with a Microsoft product, so we had to figure out a way to get that to work.
My role as the embedded systems engineer, I worked directly with the Highwander robotic hand and the Raspberry Pi 02W. I was tasked with writing code that would accurately and effectively move the servos in accordance with the data received from the HoloLens user. This required me to utilize libraries such as Pygame and PygPiod to make better demos of the robotic hand, and understanding these libraries required much more attention and a better understanding of Python and the libraries themselves. Here's a screenshot of the Tiger VNC. VNC was a way to remotely access the Raspberry Pi, and this allowed me to use it like a desktop. It would virtually connect with my current desktop. It was just a setting that had to be enabled in the Raspberry Pi configurations. And there was also the ability of SSHing into the Raspberry Pi. However, that only lets you access it through the terminal, as this allowed me to do everything that I really could ever need to do with it. And this is a demo of the Raspberry Pi sending data to the robotic hand. This is the CSV file that is being sent from the HoloLens.
Here is a demo. And as you can see from the demo, the arm was shaking erratically, but that's just more to the nature of the code that I received. Then reflections and lessons. We said we could have done better time management. We could have researched more at the beginning of the project, because the main point is that we noticed very late on that the HoloLens 2 does not track arm data, which made mapping the hand coordinates onto the arm robot more difficult, since I didn't have just generic arm data. Another point is to focus more on the communications between components to speed up development, implementation of component integration. This would have allowed more seamless integrations later on. Another point is to wait for all parts to get in before starting to work on programming of robot. This could have prevented me from changing the structure of the robot or changing the code of the robot. More points would be, again, to communicate more with the group in terms of updates to add to documentation, specifically the README. And lastly, we could have made sure that we have working equipment for the tools that we are using, such as the proper software, hardware, because my ARM robot had servo issues, and I had to grab new new servos. And I know that Matthew with the hand robot had the same issues.
Hello everyone, I was responsible for the socket server connection for our Raspberry Pi in our setup. So as you can see here on the right, this is an example of when one turns on or activates the server. It is listening on port 8080, which you can then decide to either input raw JSON input or a CSV file. In our setup, the HoloLens would have its information being inputted as a raw input and then processed. In the event that you also want to have a backup, there is the option to pre-program a list of inputs, save it as a CSV file, forward it to the server, who then forwards it to the sender client. And here we have an example of some of our code. You have a monitor quit command for a safe command on the server side. So in this case, the keyword is quit. And when you quit, it sends the message shutting down server and then actually proceeds to shut down the server. Where you have the port number, in this case 8080, as well as a buffer size input, which in this case is 65,536. This allows us to send larger bits of information through at a time to be processed while not overloading the server. As a team, what challenges or problems did we actually face? Well, for starters, this is essentially two groups that merge together to form one giant cohesion, meaning that when it came to scheduling, there were a bunch of conflicts and errors. However, in order to combat this, those members who could in fact join the meetings were able to take notes and fill in the absent members with the information necessary to continue. Another problem that we faced was hardware blockers, specifically efficient communication and turnarounds with our client, Dr. Fong, who was able to give us eventually all of the necessary components. We did in fact face problems such as a faulty servo and other similar things. And last but not least, one of the biggest issues is the fact that the HoloLens 2 is specifically set up to track hand movement, but it's not coded to track arm movement, which means we need to have a workaround. What are our next steps? Well, the first thing is to optimize the real-time movement. When the HoloLens sends information to the server, as of right now, the only safe way is to save it as a CSV file and forward the entire file. We'll have to fine-tune the data processing and infrastructures so that way it more correctly incorporates real-time movement and action. The reason why we need to tune the servo movement is to deal with cases where we had originally broken or missing servos. Doing so, we came across the issue that these servos are basic servos and not smart servos. As such, there is no coherent way to manipulate them in a way that benefits us for the movement in which we actually need to implement. Ergo, the necessity to fine-tune the different servo movements. And with that, we bring an end to our presentation. Thank you for listening, and special thanks to Dr. Fong and Professor Lin Starr.